Has anyone tried? Try ya. Not yet. Okay. Has anyone tried all? Pernah buat baru gabung. Okay. Ada yang dah try at all? Kalau belum try, I don't want to discuss yet. We'll discuss maybe after ion implantation. Okay. So no one has tried, right? No, man. So we'll move on to ion implantation now. Right. Can you see the screen? Ion implantation. Right. Okay. Good. So let's continue to the next process, which is ion implantation, which is essentially another way to introduce doping into silicon. Okay, not limited to silicon, of course, but since we are now talking about IC fabrication based on silicon as the host, so that's why we are discussing about incorporation of dopants into silicon. But if you are working on some other semiconductor devices, for instance, that also requires doping via ion implantation or diffusion, then you are actually using the very same processes, diffusion or ion implantation, but of course you need to incorporate different dopants, different dopant atoms into different hosts with slightly different behaviors, of course, but the basic remains the same. Okay, the basic of the process remains the same. So for diffusion, for instance, you still have to talk about the diffusion temperature, the diffusivity, interstitial or substitution, incorporation into the lattice. And if you talk about ion implantation, then it still goes through the very same process, which is by ion bombardment. Okay. So let's recap a few things that we have learned in the previous topic, which is a diffusion process. So we have altogether 5 questions. Let's go to the first one. Least commonly used dopants to form p-type and n-type junctions. Okay, what are the common dopants used to form p-type and n-type junctions for silicon? Anyone? You can unmute yourself or write it down. Go. What are the dopants involved? Boron. Boron is for which type? you name it and then you mention, is it for p-type or n-type with respect to silicon? Go. Write down boron, jewarium, phosphorus, gallium. Okay, for p-type, right? So jewarium, phosphorus for n-type. Can also be arsenic, can also be antimony. Okay, so it's very straightforward. It's very straightforward. So let's move on to the second question. Describe the 2 steps in the diffusion process. So what are the 2 steps in the diffusion process? How would you run your diffusion process in 2 steps?
Pre-dep and drive-in.
Okay, pre-dep and drive-in. Okay, what's the rule of the first process?
Sorry, what?
Yeah. Oh, okay, good, thanks. Right. Okay, cool, thanks. Okay, sorry, Haziq, go ahead. Pre-dep.
The question you asked, I didn't hear after what.
What are the 2 steps in the diffusion process, and what is the role of each step?
Oh, what is the rule of
Okay,
each step?
you tell the 2 steps, and then why do you use the 2 steps? What's the first one or second one? Why is it for? Okay, what's the first one? You mentioned the pre-dep, right?
Yes, pre-dep, pre-deposition.
All right. Okay. What is it for?
It is for
Why do we have to do pre-dep?
uh,
Or what do we do during pre-dep? So that will tell you why do we need it.
mm,
Anyone would like to help? Haziq, why do we do pre-dep? Or what do we actually do during pre-dep?
pre-dep. Actually, we do is dose control.
Dose control, good. So you incorporate the dopants and then you control the dose, right? Good, thanks. How about the second one?
Second
Anyone
one,
else?
Amirul.
Okay, go ahead. Yes. Apa, Haziq?
Amirul jawab lah.
Aduh pula nak jawab. Amirul, what's your second step?
Second step, drive-in is for profile control.
Yes, good. Driving is for profile control. That's where you drive the dopants into silicon and control the depth. Okay, thank you very much. Good. And the third one, how do you calculate the junction depth of the diffusion process? Okay, it depends on the process steps, right? So if you're talking about pre-dep, then your xj is equal to such and such. On the other hand, if you're talking about the profile control, then xj is equal to such and such, right? So your xj is different according to the steps. Right, after diffusion process, how do you measure the junction depth? You finish the diffusion process, now how do you measure the junction depth? Macam mana kita nak measure? Anyone? How about others? Sakina, how do you measure the junction depth? Gimana Sakina? Anyone would like to help with that? Yep.
Gaussian dengan error function ni.
All right, Gaussian error function. Let's say you are using Gaussian. So how do you explain the profile and then the xj? Where's the xj? What are the curve that is going to be involved on the y and the axis? Explain a little bit. Let's choose Gaussian, for example. You've got a curve, you've got a profile, then from there, how do you choose your xj? Macam mana? Profile dah ada?
Bentuk graf tu kan.
Yes, okay. Then?
Kalau macam Gaussian dia increase macam mana? Dia lagi macam mana? Aduh.
Well, let's say you've got your profile, the curve profile. Tak kira lah Gaussian ke arrow function ke. Dari situ, what do you do in order to get your xj?
Cari intersection dekat bulk.
Right, intersection between which curve?
Between
Be more specific. Intersection between. Intersection mestilah ada dua line kan? So between which lines?
Bulk dengan tu. Line yang aduh nama apa tak lain tu.
Dopant profile.
Oh, ha.
Okay, between dopant profile and your background doping ataupun wafer doping ataupun bulk concentration, same thing. Okay, you should mention the details, either one of the three for the horizontal line, wafer doping, bulk concentration, background doping, semua sama. And the curve one is the dopant profile. The intersection between the dopant profile and the background doping is the junction depth, right? The point there. We've discussed a couple of times in our previous class. All right, the final one. In IC manufacturing, why low thermal budget processes are preferred? Explain your answer. Why do we prefer low thermal budget processes? Anyone? Mac, how about you, Mac? Why do we need low thermal budget? Can't we go with high thermal budget? Mac? Alia? Can unmute yourself?
Sebab dia tak nak ni damage bottom layer device.
Right, tak nak damage bottom layer. Okay, any other answers? You don't want to damage the bottom layers in the device. Okay, what else? Anyone? Alia? Kenapa? Why do we prefer low thermal budget? What happens if you use high thermal budget processes?
Maybe
What
sebab
is
dia
high
tak
thermal?
nak
Yep. Yeah, Mr. Mac.
sebab dia tak nak damage circuit juga kot, doktor.
Right, okay, tak nak damage circuit. Haziq, to minimize dopant redistribution. Okay, to minimize dopant redistribution. What does it mean? Haziq, what does it mean? Apa maksud dopant redistribution? And what are the effects? Apa kesannya? If you have dopant redistribution, so what happens next? What do you foresee to happen? Haziq, elaborate sikit. Or anyone would like to elaborate on that point? Minimize dopant redistribution.
Sejujurnya
Okay. I heard someone assisting just now. Siapa tu? Tak dengar. Saya dengar sejujurnya je Haziq. Lepas tu tak dengar lah. Sejujurnya and that's it. Sejujurnya dot habis.
sejujurnya saya kurang pasti, doktor.
Alright. Siapa yang pasti? Siapa? Anyone would like to help on dopant redistribution? What is it? Why do you want to? So this means you want to avoid or you want to prevent dopant redistribution. Why is it bad? Kenapa kita nak elak dia? Apa jadi kalau dopant tu redistribute? Apa jadi?
Dia tak
Usually-
konsisten kan?
It's not consistent, right? And then whatever you design is not replicated in the fabrication. It's not translated in the fabrication. What do you design is not what you get. Okay, you design something else. You design an XJ of say 500 nanometer, but due to dopant redistribution, you might have some changes in your XJ, for example, in your lateral component, for example, in your XJ itself, in the uniformity, all the stuff, right? So that's why kita tak nak ada dopant redistribution. But the question is, can you avoid high thermal budget processing in wafer fabrication? Can you avoid high thermal budget processing or processes in wafer fabrication? Can we avoid at all? Boleh elak ke? Of course, we prefer low thermal budget, but can we avoid at all? At what temperature do you run your oxidation? At what temperature do you run your diffusion? At what temperature do you anneal, for instance? Kita boleh nak avoid, we cannot avoid, but you have to control. Okay, you cannot avoid because say if you don't run your need just to relate between different processes. What happens if you try to avoid high thermal budget process in oxidation, thermal oxidation, then you choose to run your oxidation at very low temperature, for example, at 400, 500, instead of at 980 degrees C. So what do you expect to get then? Sebab you nak avoid high thermal budget, so you run thermal oxidation at low temperature. Apa yang akan paling senang jadi bila you run at low temperature? What do you get? Oxidation at low temperature. Anyone? You have to relate. Nanti kita akan belajar after you finish all the processes. We're going to learn about process integration. How do you integrate all the processes? Oxidation, litho, etch, diffusion, implant, thin film oxidation, thin film deposition, coming together in order to fabricate the final devices. So at that point, you're going to learn that this process, the quality depends on this, but you cannot go so high because of blah, blah. But if you go too low, then you're not going to get this. So they are all interrelated. So that's called process integration. There's even a department for that, process integration department, where you get to oversee all the processes in the process flow, in the way that how do they affect the whole quality of the devices. So what happens if you run oxidation at low temperature? You're supposed to run at 950, for example, degrees C, but you choose to run at 600. Apa jadi? Anyone? Relate back to your knowledge in oxidation. Apa jadi bila you run oxidation at low temperature? How about Kali? Kali, what's going to happen if you run your oxidation at low temperature? Apa jadi low temperature process, oxidation? Do you get to oxidize the silicon dioxide on silicon?
No,
Anyone?
yes, sir.
Not what? Sorry, am I wrong?
No oxidize.
Not
The-
oxidize, sure.
The
Can you
silicon.
oxidize your silicon dioxide at room temperature?
Yes.
Then can you oxidize your silicon dioxide at 600 degrees C?
Yes, but the thickness is not it.
Yeah, right. So you run your oxidation at low temperatures, so you're gonna get lower oxidation rate, right? So go back to the Deal growth model, right? Dia punya thickness yang akan form pun akan lower lah, because you can go back and check the curve where we discuss the temperature against the thickness for wet, for dry. Okay, lagi lower the thickness, lagi lower the temperature, the lower the thickness, right? So if you're supposed to run at 950 degrees C, but you choose to run at 600, for example, then the thickness, the oxidation rate will be way smaller. Okay, as a result, to be able to grow the very same thickness, you need longer time. Okay, so that will then sacrifice the throughput of the whole process flow. Throughput, number of wafers per hour that you can finish by a certain specific process. So this is the thing that you have to understand and relate, right? You know, when you learn all the processes later on, especially when we talk about process integration. Okay, done. So let's move on to ion implantation. It's another form of process that we use in order to dope the silicon. Okay, you can diffuse, or you can also ion implant your dopants into the silicon. So it was used for atomic and nuclear research, introduced back in the 50s, introduced to semiconductor manufacturing in the 70s. It's been around for 50 years, right? For about 50 years, close to. So Ion implantation involves independent control of dopant profile. We discussed briefly about the profile introduced by diffusion process versus the profile introduced by ion implantation process. So we know that so far that when you use your diffusion process, you will not have a very good control over the junction profile, the junction depth, the distribution on the diffusion process. We've discussed about the lateral component, the horizontal component, due to diffusion of the dopant into the side as well. So you will then have some profile under the mask, okay, because of diffusion. On the other hand, if you run your doping process by ion implantation, you can control your profile better at the areas that you want to dope. So anisotropic dopant profile, so it's more directional, so that means better control. Macam anisotropic etching, right? Better control, but you still have some side component, but the dominant one will be the vertical component. So in this case, you're gonna have a very good control of your profile. So easy to achieve high concentration of heavy dopant atoms such as phosphorus and arsenic, especially if you want to dope your dopant at a very high level, then ion implantation is more intended, right? So let's recap on the doping process. So in this case, so on the left hand side and on the right hand side, we have our silicon dioxide mask. Okay, so mask is where the area that you don't want to dope. Okay, you don't want to diffuse, you don't want to implant. So that's why you have your mask with thickness exceeding minimum thickness. Kalau tidak, no point. It will just dope anyway. And then your polysilicon is here. So assuming this is your gate now, polysilicon gate in a MOSFET structure, for example. And then you have your oxide down here, gate ox under the polysilicon. And then you have your P-type silicon, and then you want to introduce your PN junction. Okay, PN junction. So here will be the N+, the areas that you want to implant or you want to dope by ion implantation. So in this case, if you dope this N+ on the left and on the right of the gate, then you will form N-type transistor, N-type MOSFET. Sebab dia punya channel ni is formed by N-type, N+ and N+. Your substrate is P-type. Okay, so these are the areas that you implant, and these are the areas that you block, and also the central part. Right. So let's just recap. If you dope your channel, in this case kita sebut channel. Kalau kita nak relate dengan MOSFET, then we're talking about channel formation. So you have your mask on the left, on the right, okay. And then if you talk about diffusion process, after the diffusion, you're going to have some depth as intended, and then you will also have the side component due to lateral diffusion of the dopants during the process. On the other hand, if you dope your silicon using ion implantation, you still need to have your mask on the left and on the right, and then say the junction depth is comparable or same to the diffusion one, but then you don't have the lateral component on the mask because the profile is implanted into. Okay, there's no diffusion, it's just macam embed, bombarded at high energy, middle energy, or low energy. But the idea here is bombardment. The bombard here is very precise, very precise. Okay, so that's how you control your profile. Okay, some differences of diffusion against ion implantation. Diffusion involves high temperature hard mask. Implantation runs at low temperature. It uses photoresist as the mask. Diffusion involves isotropic dopant profile because you have your side component while diffusing. On the other hand, if you run your ion implantation, you're going to have a more anisotropic dopant profile because it's very well in control. You cannot independently control the dopant concentration and junction depth to some extent. It's not entirely true because you still can control, but the control will not be as accurate as the implanted junction. Okay. On the other hand, you can precisely control, independently control the dopant profile and the concentration and hence depth. Diffusion is batch processing. You can watch the video I uploaded on Elan. dia masuk sekali kan, masuk sekali banyak-banyak tu wafer tu. And implantation can be batch and single wafer processes as well. So boleh run single, boleh run batch. So again, another differences. For implantation, beam current and ion implantation time control the dopant concentration. Okay, so if you talk about ion implantation, then you control the beam current and implantation time. There's also another factor like ion energy. You can also use dalam fab biasanya kita akan ada high energy implanter, middle energy implanter, low energy implanter. So they have different energies that can embed your dopants at different depth. Okay. And then your dopant profile is anisotropic. Okay. So examples of the ions that you can use in order to run the implantation process, we've discussed briefly just now, exactly the same like the diffusion. Okay. For P-type, we normally use phosphorus, arsenic, antimony. For P-type, we use boron. Okay. So schematic representation of your implanter. So wafers coming in. So this is your implanter represented by a simple box. So your gases and vapors coming in as the dopants to be implanted into the silicon. So you can use your ion, either it's boron or phosphorus or arsenic. Ion energy can also be chosen, whether it's going to run at high energy, middle energy, low energy. You can also select the beam current, okay, to run the process. And then the moment you've done your implantation, the wafers need to go to the next step according to the process flow. So this is another example of the inside of the ion implanter. So you have gas cabin to supply the gas, then ion source in order to ionize the incoming gases so that they can be accelerated at high energy towards the target. In this case, the silicon. So tengok sini ada electrical system, ada vacuum pump. There's also an analyzer magnet in order to bend the path of the ions. They can bend 270 degree. Okay, they can bend, they can pusing and hit. So the beam line is here. Yang dark blue is the beam line. And then electrical system, vacuum pump, and your wafers are here on the other end of the system. Okay, so the moment the gases are ionized, so one specific gas is ionized, for example, phosphine ionized to phosphorus with ions, so accelerated, and they can follow path ni, and then bend, and then go to, so it's going to become a high energy one. And then it's going to hit the wafers at high energy in order to be bombarded. Okay. So mechanism, while doing the implantation, ions will penetrate into substrate. So just assuming that you're running phosphorus, and then phosphorus will penetrate into the substrate. In this case, the substrate is silicon, and then they are going to collide. The ions are going to collide with the lattice atoms. Okay. They can collide dengan silicon atom in the wafer, of course. And then the ions are gradually losing their energy and stop. So bila they collide, they can losing energy. And then they will not break instantly, but they akan gradually losing energy. They akan masuk dalam lattice tu, slowly, and then eventually lose all the energies and stops. Right? So there are two stopping mechanisms involved. So the first one is called nuclear stopping, where collision with the nuclei of the lattice atoms are involved. So it's going to lead to scattering significantly, scattering of the ions in the lattice. Dia akan, bila dia langgar, kita akan tengok dia akan change direction. Dia akan, sebab dia ada scattering, dia akan scatter into multiple directions. This stopping mechanism, the nuclear stopping, causes crystal structure damage. So when you do your ion implantation, when you do your doping by implantation, it's going to cause crystal structure damage. Maknanya kalau you start your wafer, you start your fabrication with 100 silicon 100, then your lattice will be damaged to some extent after the implantation process because of the high energy bombardment. Okay. The second one is called electronic stopping, collision with electrons of the lattice atoms. Okay, dia collide dengan electron of the lattice atoms. Incident ion path is almost unchanged, so dia punya scattering tu is not that significant. Dia ada sikit-sikit je perubahan. Energy transfer is very small due to the nature of collision. Crystal structure damage is negligible. Okay, it's very, very small in comparison to the first one, nuclear stopping. That one is very, very damaging. Okay, the second one is negligible. Okay, so for example, if you want to look at the stopping mechanism that we've discussed, so ion, just imagine this is your silicon, and the ions are coming from the front. Front here means from the left. So if you go back here, yep, so that means the beam is coming from the front. Beam is coming from the front, but on the other image, we rotate the image to 90 degrees anti-clockwise so that you can see it's coming from the left, but it's actually coming from the front though. Okay, so ions are embedded into silicon, experiencing random collision. So there'll be channeling of the ions where you have minimal change of directions of the ions while they are traveling into the lattice. So you can see the arrow here is very minimal change. So effectively into one direction as intended, as the way we implant. On the other hand, you may also have back scattering, especially when you have a high scattering occurrence where the atoms will be scattered into various angles. In this case, you can see that upon the first incidence is going to be scattered at about say 40 degrees, more or less 40 degrees from the original path, about 30-40 degrees perhaps. And then upon the next collision with the atoms, it's going to experience some back scattering as well. Okay, so it's going to be random in nature, but you can design based on the beam current, based on the ion energy that we're going to use in the process. So it can in fact be simulated. Okay, so stopping power against ion velocity, nuclear stopping against electronic stopping for three different phases. And then ion beams coming from the left. Then you can see the trajectory of the ions into silicon, and this is the distance of the distance into silicon. So your x0 here, the origin is the surface of the silicon, and then going to the right means going into silicon, right? So say this is your projected range designed during your recipe creation. Kita create recipe. So every proses yang ada dalam wafer fab, in fact dekat backend pun, semua ada recipe ya. Some cases we call it job file. You create the recipe. In some cases you call them process recipes where you define temperature, time, ion energy, beam current, and whatever related to any specific process. So based on the recipe created, so this is a projected range of the ions when they are colliding into silicon, right? Traveling into the lattice. And this is example of the ion trajectory into the lattice. Okay, there are the collision, there are some change of direction. So it's not going straight. Okay, it's not going straight. So this is again ln of concentration of the ions. And then this is a projected range, and then this substrate surface where x equals to 0, and then it is going into the silicon. And you can see here when you run your implantation, so this is projected range, and then after that it's going to go down. Okay, but this is not it depends on the recipe. It depends on the recipe. If you run for high energy process, then you can actually embed the atoms, the ions in the silicon rather than close to the surface. So if you run middle energy, then it's going to be lower in terms of energy. Then it's not going to be embedded so deep into the silicon. Okay. So projected range against ion implantation energy. So you can for different dopants, for example, boron, phosphorus, arsenic, and antimony. Okay. So you can see here that the projected range is proportional to the implantation energy, and you can choose to run from your implantation from low energy implanter, middle energy implanter, high energy implanter, for example, and they can give you different projected ranges. Okay, if you go for higher side, higher energy, and then you're gonna get a higher projected range. Okay, for example, if you choose say phosphorus, so if you choose phosphorus, if you run the process at 100 keV, kat sini kat tengah phosphorus, then the depth is going to be somewhere 0.1 something, right? 0.15 perhaps, okay? Micron, okay? Micron, so 150 nanometer. On the other hand, if you run at 500, for example, 500 keV, 2, 3, 4, 5 kilowatt here. So your projected range will then be around 0.7 micron, okay, 0.7 micron. So in comparison to 0.15, say, so you are adding, you're getting extra 500 or so nanometer due to the increase in the implantation energy. So that's what the high energy implanter does to you. So barrier thickness. So barrier thickness means this. If you go back to the barrier, just like the mask. Okay, for example, this one, photoresist ini. So the barrier has to exceed certain thickness in order to successfully block the ions. Kalau tak exceed certain thickness, minimum thickness, then it won't block the ion, just like the way you run your oxidation. Okay, sorry, the diffusion using silicon dioxide mask. Kalau you tak guna certain minimum thickness, then you're gonna dope it anyway, right? Let's go back to the minimum thickness. Right, so if you're running a 200 keV ion beam, ion implantation process, so 200 keV, then if you are implanting phosphorus, okay, look at this curve, the V-shape, lebih kurang V-shape phosphorus, then if you use your mask as photoresist, kalau you pakai photoresist as the mask to block the implantation, so that means you can use various masks: silicon, silicon dioxide, silicon nitride, aluminium, photoresist. If you use photoresist to run 200 keV ion implantation process to implant phosphorus into silicon, that means you're gonna need at least 0.82, 0.8 something, 0.8 something micron of photoresist in order to block phosphorus from doping the mask areas. Okay, that means if you don't have your thickness to be more than 100 nanometer, katakanlah you punya minimum thickness is only around 0.6 micron, then that means it's not going to block the implantation from continuing, right? So you're still going to have phosphorus in the mask areas, perhaps at lower concentration, but you're going to have them under the mask, okay, because the thickness is not enough. So that's the whole idea, just like the way we discuss silicon dioxide masking for diffusion process. So implantation process also involves channeling. So if the incident angle of the ion is right, then ion can travel long distance without collision with the lattice atoms. Okay, so kalau you manipulate the angle properly, then it's going to be minimal collisions. It causes uncontrollable dopant profile. So if you have things like this, condition like this, since there's no collision, that means you cannot control the depth very well, because it's just going to go through the lattice indefinitely. Okay, so if I tengok kat sini, say this is your lattice, and then your angle of incident is here. Okay, so it's coming straight through the lattice, okay, and very few collisions experienced, and as a result, you cannot control the dopant profile very well. On the other hand, if you run at some angle, in this case, for example, lots of collisions experienced by the ions going into the lattice, through the lattice, so you can have a better control of your implanted profile. Okay, so that's why it's very, very crucial to understand the effect of the incident angle during implantation. Okay, another example of the same thing, channeling effect. If you position it in such a way like this, they can go through straight. Then you're going to have channeling of the ions through the lattice, and you cannot control the profile well, right? If you, on the other hand, if you control the incident angle of the implanted ions at, say, theta, like this, then the ions are going to experience considerable amount of collisions through the lattice, and that's where you get to control the dopant profile. So there'll be post-collision channeling as well. Okay, contoh collision yang ada. So kalau ada collision, then you're gonna see your ions implanted at some angle, theta in this case, scattered at some angles, scattered at some angles, scattered at some angles. So collision leads to channeling eventually, right? Walaupun we have positioned the theta very well earlier on. So due to channeling after the collision, collision, then dia dapat angle cantik ya untuk masuk through the lattice, and they will still be channeling after the collision. That's why we call it as post-collision channeling. Okay, and then at some angle dia akan tukar direction to some extent, and then there'll be collisions again next. Okay, so this has to be simulated before you run the actual process. So ways to avoid channeling effect. Tilt the wafer, say 7 degrees is the most commonly used angle. Okay, maknanya the incident beam is coming at 7 degrees off angle. Okay, you perpendicular, then you mean 7 degrees off angle. Okay, now from the normal to the surface. Tilt 7 degrees, most commonly used. You can use screen oxide, pre-amorphous implantation, germanium can be done as well. Shadowing effect, you can also block your ions using structures. Sebelum ni kita belajar shading effect kan? Where did we learn shading effect last time? Diffusion, right? Diffusion. So you get to below the structure dekat atas, then certain areas will be blocked, and we're going to come back to that when we discuss thin film deposition later on. There kind of shadowing effect juga. Ion can be blocked by structures, rotate wafer, and post-implantation diffusion. So to avoid channel, you can also rotate the wafer so that the distribution is more uniform. And then you can also do diffusion after post-implantation. See? So this is where I said that in the actual case, sometimes, most of the time, not sometimes, we combine diffusion and implantation in various ways in order to do various things, okay? Various ways for various things. So it's not strictly related to, it's not strictly diffusion or strictly implantation, but they can be combined in many different ways to achieve a different objective. So in this case, in order to minimize post-collision channeling. Okay, channeling, shadowing effect. So if you want to dope this green region, dope region, and then you have polysilicon gate there on the wafer, and then gate ox, and then you tilt the angle, say at 7 degrees, and then these areas close to the polysilicon will be shaded. Okay, dia akan ada bayang, so it will be shaded because the ions coming from that angle, 7 degrees, so that you don't have channeling, but as a result, you're going to experience shadowed region ataupun shadowing effect. Okay, kita nak elak channeling, kita dapat shadowing pula. So kalau you buat straight, then you probably have channeling, but then there's no shadowing. So you have this, so you can see that the dope regions are not completely dope. So what you can do next is you can do after anneal and diffusion. You can also diffuse this region as well. Okay, can be done. So implantation is a high energy process, therefore is very damaging. Sebab dia high energy. So implanted ions transfer energy to lattice atoms to break free. Okay, bila dia transfer energy, they can conserve. When energy transferred from the ions to the lattice will cause the atoms to break free from the lattice. Okay, free atom collide with other lattice atom yang release tadi tu dia akan collide dengan other atom to create more free lattice atoms. Okay, dia akan ada macam domino effect lah, langgar. The damage continues until all free atoms stop. Sampailah energy itu habis, dia akan habis. Then only the collision will stop, and therefore the lattice atom will not be broken anymore. So one energetic ion can cause thousands of displacement of lattice atom. So just imagine one ion bombarded at certain energy, since the nature is high energy atau middle energy, say, then that can cause domino effect. Langgar, release, langgar. So that in total, the collision and the release and the post collision akan cause damage to the lattice. Okay, so banyak atom akan displace from the original position, causes lattice damage. Okay, so for example, if you use light ion, the damage is still there, but then the effect is more minimal, because the ion energy tu is not that strong, because it's a light ion to begin with. Macam kalau you main rugby ya, for example, you main rugby, kalau you kena langgar dengan player yang badan kecil sikit, tak terasa sangat, mungkin terinjak sikit. Tapi kalau player apa ni, New Zealand punya All Black then habis, terlentang heavy ions, heavy ion langgar, then that will cause more damage to the lattice atoms. So the ion collide with the lattice atom and knock them out of the lattice grid, so they'll be displaced. Okay, implant area on substrate becomes amorphous structure. So before implantation, we have a 100 silicon, for example, that you started with 100, then crystalline arrangement is infinite, perfect arrangement. And then after the implantations, due to the dislodgement of atoms from the lattice, from the high energy collision, so you will cause the implanted area to be damaged. And this will change the lattice from monocrystalline to amorphous. Okay, so monocrystalline on the left, indefinite arrangement, and then you can see amorphous. There's no specific arrangement of atoms anymore after the implantation. So that's why when you have the damage in the lattice needs to be annealed. Okay, anneal tu ialah proses yang kita run wafer at high temperature in order to restore the lattice damage. Kita nak repair balik daripada amorphous ni, after the implantation it becomes amorphous. You want to restore the original condition like this, monocrystalline. Kita nak restore balik, then the process that we need to do is called annealing. And again, it's a very high temperature process in the range of 900, 1000, short time, long time. And that will, again, induce high thermal budget processing, right? The way we discussed now. But this cannot be avoided, because or else you won't be able to restore the original lattice condition. So dopant atom must be in single crystal structure and bond with 4 silicon atoms as intended. Thermal energy from high temperature helps amorphous atom to recover the single crystal structure. So this can only be done by high thermal energy. Okay, high thermal energy means you have to run your process at a very, very high temperature. Okay, at very high temperature, and that again introduces the lattice damage, the thermal budget into the process. So we're almost done. Let's just see what is the thermal annealing doing to the lattice. So this is your lattice atoms, and this is dopant atom. Lattice atoms are the one in gray. Okay, dopant atom is what you have implanted from your implantation process, and the process is done. So now you've got your atom here, there, right? So you've got your 5 atoms all together, for example. And then you can see that the silicon atom ni dia dah bertabur. So then we have to do thermal annealing in order to restore the original condition, like monocrystalline. So let's see what happens. So if you run the thermal annealing over time, you run sekali tapi you run long. So during the process, it will slowly restore the lattice. Okay. So see the first case is only first line becomes well arranged, macam monocrystalline. And you go to this, if you go to the process longer, if you run the process longer, then it's going to repair the damage. Dia dah jadi second line, dah jadi restored like the monocrystalline. So now you have 2 rows recovered as monocrystalline. Then you rerun the process longer. You're going to restore the 3rd row, 4th row, 5th row, 6th row, 6th row, 7th row. Okay, so you end up having the original condition like this before implantation. So that's what is done by the thermal annealing. So that's why you still need to run high thermal budget process in order to achieve something in the process flow. Okay, So in this case, the thermal annealing is needed to repair the defects, if you like. Okay, dia punya essence repair defects, tapi defects tu caused by high energy implantation that has caused the monocrystalline lattice to be amorphous after the implantation process. Then kita hantar after implant, hantar wafer masuk thermal annealing to repair the defect so that the wafers now become monocrystalline. So before annealing, in summary, like this, amorphous. Before annealing, after implant, before implant, monocrystalline. After implant / before annealing, amorphous. After annealing, monocrystalline. So monocrystalline, then damaged by implant, then restored by thermal annealing. Right? Yes, done. We're done with ion implantation process. So is it okay so far? Do you understand the essence of the process? Is it okay? Boleh ke? Is it good? Ada soalan? Semua faham? Faham ke? Tak ada jawapan kan? Saya tak tahu faham ke tak ni. Okey ke?
Okay, Doktor, just kena buat revision sikit kot before completely understand.
Yep. Okay. All right. So revise accordingly. So one more time, please do the diffusion calculation. Diffusion punya slide tu, final slide, please do the calculation, then we discuss. Kalau you tak attempt lagi, then no point discussing because I'm just giving you giving you answers. Macam tak discuss lah. So yeah, can we discuss tomorrow? Please go and attempt today, and then we discuss first thing during the class tomorrow. Then we move on to after implant will be thin film deposition. Okay, thin film deposition. So you're going to learn about PVD, CVD, thermal evaporation, sputtering, any CVDs. Okay, thermal thin film deposition. We're going to go to process integration, where you combine all the processes together and see how do you connect one to another one. Right? So I'll see you tomorrow then, 11. Okay, bye bye. Take care. Assalamualaikum.